something actually noble with it. So, oh, didn't get this one queued up. Okay, 103 is what we're on, and this one's 2 pages. And this one, I apologize, I didn't quite finish the notes before I had to come to class, so the last part won't have, it has a sort of ellipses at the end, and I'm going to talk us through that part. I was trying to draw another cool figure, and figures always take longer to draw than you think they will, so. Okay. Excellent. So we are on lecture 103, computer architectures. So if we descend from high-level programming languages like Python to low-level languages like C, remembering table 1.1 with its descent, then continue to descend, we begin to require more hardware-specific considerations. Computer architectures are descriptions of this sort of more hardware-specific considerations, down to a fairly concrete level, stopping somewhere above the actual physics of the whole thing. So a computer architecture doesn't really get into, typically, except for very exotic ones, it doesn't really get into like the physics of how things are working. It'll look at a sort of functional unit, it's called, that does something from a logic point of view. It's a circuit that does something, and we don't really usually get into that part of it. That's more of like a digital circuit design study as opposed to computer architecture. So computer architecture uses these sort of building blocks that aren't totally down to the sort of fundamental physical processes, but sort of these functional units that you can build up and make things happen. So I have to say computer architecture is it's so fascinating and so complicated. There's a lot going on because it's mixing these, it's trying to allow us to do really complex things on, circuits, right? And so it's trying to take these, minimally functional blocks and turn them into things that can do lots of stuff. And what happens is there are lots of ways you can do it and make something work, but making it work well, optimizing this whole thing, that's very, very complicated. And that's what this is all about. And it's really cool. Although we only have a little bit of time to talk about it, we'll try to describe it at sort of a high level. Embedded computer programming contacts the computer architecture much more than does personal computer programming. In fact, the C language gives us access to different aspects of it. So we're actually going to be able to interact with some of this computer architecture to a point. Not down to the assembly level language, but assembly language level, but we will get pretty close in certain aspects. Consider the 4 primary components of a computer that follow. So these are the classic 4 primary components of a computer. The central processing unit is the first. So the CPU consists of a control unit, which can be thought of as being the sort of brain, and a data path, which can be considered sort of the brawn. It's a very, very rough way of putting it, but it's sort of a way to think about it. The control unit receives machine code instructions from memory and controls the other components to perform corresponding tasks. Okay? So it's sort of like the boss of the whole thing. It's telling everything else what to do. Okay? The data path, so the other part, consists of functional units such as registers, which are the fastest, smallest capacity memory, buses, which are intra-computer communication systems. So intra meaning internal, So it doesn't, not outside the different things, but inside the computer communication. And arithmetic logic units, so ALUs, that can perform very basic arithmetic and logical operations. So figure 1.3 gives us an illustration of an ALU. So what an ALU is actually, it's a circuit, and you give it a couple things, and it gives you a couple things. So you give it an integer operand, maybe in both slots. This is something that would be like, for instance, a sum. It's a good example of one. So you give it an integer a and an integer b. When I say you give it, what I mean is the control unit tells memory to send over to the ALU an integer from memory at a certain address. So from this address, send it to A. From this other address, send it to B. And then from the control unit, it'll give it a status and an opcode. So for instance, sum. And you'll get an integer out of it. So if this was like 2 and 3, you would get 5 out. And status is going to tell you, like for instance, if there was like finished the operation, for instance. And
you can also display like negative and positive, or
the status I don't think is usually used for that. Status is so the integer result can encode the sign. So the sign is typically encoded into the number itself. So we'll talk more about that in number systems discussion next time. But yeah, it's usually embedded into that. So this is coming from memory and going back to memory. Whereas this is coming from the control unit, and the status is being returned to the control unit. So memory flow, it flows in from memory and it goes out to memory. So, but the control unit has to be told, okay, did it. And then it says, okay, do this one now. Did it. Keeps moving, shuffling through memory contents, data, we usually call it, or instructions, but typically data in the case of an ALU.
So status can be fail, success, or error?
It depends. I mean, it depends on the ALU. It depends on the system. Yeah, I mean, those are potential status reports back to the control unit. But the control unit is typically it's concerned about timing. A lot of it is like, what's this ALU doing right now? Telling me, because then it knows if it can send it another instruction or not, or when it can. So that's primarily what it's doing. I don't think there's a lot of concern for error at this level. I don't know that there's error checking in ALUs. Usually it's like finished, completed the task that you gave me, the last task that you gave me, completed. That's the primary use of it, is for timing and not so much for errors that happen. Error checking usually, I don't think, now it's hard to generalize this, and that's part of the difficulty here is that we're talking about an abstraction and not like an actual thing, but not that I'm aware of, do they usually do error checking in ALUs. I mean, now I say that, probably somebody does it, but not that I know of. Okay. Great. So ALUs can perform these very basic arithmetic or logical operations. So it could, possibly be like and, or, else, if else, like that sort of thing. So that's those. The control unit has this sort of, telling everybody what to do function, and the data path is like these, like ALUs and buses for communications and registers to like hold a number for just a moment before we take it and add it to this other number. So we'll talk a little bit more about registers. Will be something that we'll interact with some at in C. You can actually interact with the registers directly. It's pretty cool. So memory stores data. Okay. So that's the main thing that it stores. For example, numbers, files, etc. The other thing that it can store is instructions. And instructions are the things that the CPU is going to do, right? So sometimes it's data and sometimes it's instructions, but there's nowhere else for instructions to be, right? So it has to be stored in memory along with the data. So in order for the processor to know what to do next, it has to get an instruction from memory. And then it does that instruction, looks for the next instruction, but the things that it's doing also take data in from the memory, and it writes it back out to memory too. So, so memory is a really important part of it. Numerous forms of memory exist, but the primary variable of interest is that of speed of access, and that is reading and writing. So how fast can you read from the memory and how fast can you write to the memory? Faster tends to mean less capacity and more expense. Permanence is another consideration. Some memory, called volatile, lose their state when they lose power. Typo in there. While others, called non-volatile, do not. So some memory, when you lose power, it loses its state. So that's really bad if you want it to stick around. So volatile memory is not permanent, and so it's only holding it temporarily. So I think that we're all familiar with some of the, and we're going to talk more about different types of memory later, so I don't want to go into too much detail here. But in your PC that you're familiar with, you've got the either the hard drive or now the solid state drive, right? Which is the like pretty deep storage, right? Like slowish, but like, and it's permanent, right? You lose power to it, it's still there when you turn it back on. A CD or a DVD doesn't need to be powered to have a certain state, right? It keeps that there. And then there are other types like RAM, for instance. So RAM is much faster to read and write from than like a hard disk or even than solid state drives, but it's smaller, right? And it's more expensive for how much space you get. And then there are even other types that we'll talk about that get closer and closer to the processor that are faster and faster to read and write from, but are smaller and smaller and more expensive if you want bigger ones. And down to the level of the register, which is built right into the CPU, that it stores that little bit of like just a handful maybe of numbers to do the next thing with. So it's the memory sort of hierarchy that they talk about is like it gets smaller, more compact, and faster, and more expensive. And then as you go up, and it's like, okay, slower, larger for less money sometimes. And then there's a certain point where like huge costs more. But so those are the different sort of levels of memory. And then there's volatile, non-volatile. So things in registers typically are volatile. Things that are in RAM are volatile. But when so when you reboot your computer, whatever was in RAM is probably gone. Unless, like, you could have something that was like saving it from RAM to the hard disk before it crashed. It might have been able to dump it. And that's like when Microsoft Word tries to recover the file for you or whatever that you were working on. It stashed a copy of it before your computer crashed, and it knows that you never saved it. So it's not like it had it in RAM still. It's wiped out from RAM, but it had it saved it on the disk. So then it's like, do you want to keep this? Do you want to recover this file? And you say, thank God I got to recover this file. Okay. Good. These considerations, and there are a lot of them, lead to complex optimization considerations, the use of the same word, in which different types of memory are used within the same system. Roughly speaking, data or instructions that are most likely to be read soon are moved to faster, smaller, more expensive memory. So it gets closer and closer to that processor, and the memory is faster and faster to get to. Ideally, all of the data and instructions that you need soon are right there at hand. Sometimes it's got to load in stuff from RAM frequently, but then it's got to go all the way to like your hard disk. That's going to take it longer because it's waiting around to get it through the pipeline of memory. It's waiting for read and write. So one of the things that really sped up those machines in the lab, those PCs in the lab, was to do solid state drive upgrade. Because the bottleneck was just hard drive read and writes. And solid state drives are much faster to do those reads and writes. So when we got the solid state drives, performance just went through the roof. So we got rid of that bottleneck. If we had added a bunch more RAM, probably wouldn't have changed that much, because the real bottleneck was when you pull in your user profile and stuff, it's loading stuff from the network and it's writing to the hard drive, and it's taking forever to do that. So the hard drive is just in there churning for 5 minutes. It drove me crazy. I'm really glad that we got that upgrade. Okay, inputs are data from devices other than the computer, such as keyboards, sensors, and remotely communicated commands via, say, the internet. So stuff coming from outside. You plug in your keyboard through the USB. You're hammering stuff in. That's going to be inputs to our micro processor, our embedded system. We're not going to connect a keyboard to it. Our development system will have a keyboard to write the C code, but when we're actually interacting with our program in the embedded environment, we have the keypad, right? So the keypad is what we're going to use as our input to the system. Also, there are going to be sensors as well, right? So in the system that we have an encoder, for instance, that measures the angular position of the shaft, and that is going to be another input to the computer. Okay. And then finally, outputs. So outputs are data sent to devices other than the computer, such as displays, printers, and actuators. For example, in our system, it's going to be a motor. We're going to send it, really a driver for the motor, but we're sending a signal out from the computer to interact with the world, and that's considered an output. So those are the four primary components of a computer. And let's take a look at this figure and see if we can interpret it a little bit. So here are the four components. So the control unit and the data path are the CPU, right? So together they make the CPU. I broke them out here because they have a lot of interaction between them, so it makes sense to sort of split them off. Input and output are pretty easily shown there. So there's usually a part of the computer that controls this input and output, like a bus or multiple buses, so for communication. And then we have the memory as well. So what I thought we would do for the rest, for at the end of this, is to sort of walk through this and follow. There's a lot of arrows here. So let's follow what you would do if you started with like a plus, and we're just gonna roughly sketch out what would happen if you started with the C code plus operator. So process that a C code plus operator would undergo from a main function down to interacting with the computer components described in the figure. So you think about C code. So like the C code plus. Operator. So that's happening. We'll kind of try to draw what the figure is I was thinking about drawing. So this is going to go down, and it's gonna get, first of all, compiled, right? So a compiler is going to compile this thing into, let's say it compiles it to assembly language. So compile, and you get assembly language. And the plus, so for, I looked up the instruction set for our Cortex A9 processors, which we have on board the MyRios. So in that instruction set, they have the add instruction, which a lot of times it's called add because it makes sense. So it would be add. So after we compile, it would be add. And sometimes it's called the assembler. Sometimes a compiler will go all the way to machine code binary, but sometimes there's an extra step here called the assembler, where we, well, I guess assemble would be the right word to use there. Assemble into machine code. So this is, I didn't get a chance to run down exactly. So the machine code for add is found in the instruction set documentation, which is 2,700 pages long. I downloaded it, and I hadn't quite gotten through to figure out what the binary sequence is for add, but it started out like 0, 0, 1, and then I don't remember the others. Is like, anyways, but it's going to be 16 bits long. 1, 2, 3, 4, 5, 6, 7. Jeez. Anyways, ... Binary. It's going to be a binary number, 16-bit for our processor, and yeah. So that is the level it got down to. It's an instruction. Now, there's going to be more involved too, because it's going to have to talk about, what are the two things you're adding and all that. So it's kind of a simplified view, but we're just kind of trying to get an idea of kind of how it goes from this high level down to this low level. So now we're kind of, here we crossed a barrier, right? We went from general, so general purpose we called it, to below this is now machine specific. Software, or I would say, software. And then we start interacting with the hardware. So let's go up to our figure here and talk through what that would look like. So the first thing would be that it would be in memory, and the control unit would pull from memory an instruction. Okay, so it would pull this binary machine code thing. So I want to say so I'm going to call the control unit CU. Pulls from memory an instruction, and then it's going to send out, according to that instruction, it has certain rules that it's going to follow based on what the instruction says. Like for instance, if it says to add two numbers that are in these other two addresses in memory, then it's going to tell the data path to, for instance, take an ALU and pull data from memory and from maybe those two addresses. So it will tell memory to send data path certain addresses. Data path will be, say, have like an ALU inside there that will take those two numbers, and it will also give it the instruction add, and it'll return some data. And what it does to that data, it depends on what the control unit tells it to do. So it's either going to go back to memory. Often that's what it does. It goes back to memory. That's done. Or it will go to I/O. Okay. For the plus, that's probably it could also be pulling. So for that plus, the two addresses it was going to add together, or the two contents of those addresses was going to add together. It could pull one of them or both of them from I/O as well. So like it could come from an encoder value or something like that, or a keystroke. So it could come from I/O or it could come from memory. I would say oftentimes it's going to come from memory. I would say most of the time you're coming from memory, but it might come from I/O also. So data path is sort of, doing the actual operations, right? It's the circuitry that's doing the actual operation. Control unit's telling it what to do with this control signal, and then data path's telling it what's the status. Data path is sending back what the status is. I/O is sending its status. Control's telling memory what to do, telling data path what to do, telling I/O what to do, and that plus got sort of pulled from memory, let's say, and then dumped back to memory. Maybe whatever the result was needs to be, and then maybe the next instruction is to take that result in memory and send it to I/O, for instance, which could happen as well. So data path would pull it from memory and send it to an I/O. So it's really everything depends on what you're doing. But that's just sort of like an idea of what a plus would do. The control unit's sitting there above everyone, bossing it around, like send this address of memory to this part of the data path, and then data path do this with that thing from memory. And then I/O, what do you do when an input comes in? What do you do to output? What are you trying to output? Where does it come from in data path? So, yeah.
So how the input go to the control unit? I mean,
So the control unit is so probably what the input would do is input would come in, control unit would tell it, would send it to the data path, which would write it to memory. Maybe do something with it depending on what operation it would do, and then send it to memory for storage. So the control unit isn't really ever it doesn't really hold on to those commands. What it's doing is it's figuring out from memory what the next thing is, instruction is to do, and then it knows the right steps. It's like interpreting the next instruction and then telling its team of devices what to do with that instruction that just came down.
Do you have an example like just like numbers added to each other? Let's say.
Yeah, so that would be, for instance, the control unit would tell memory to send data path maybe 2 addresses in memory. So like memory.
Just an operation all in memory, yeah.
So it doesn't happen all in memory. It takes those, it sends them to data path. And data path actually adds them together. So like over here, the 2 numbers are stored, let's say. So number 1, so yeah, so like numbers 3 and I forgot 2 that we used. So 2 and 3 are in memory. Control unit says memory, send them to data path. So they get sent over. And then it goes, in data path, it goes through an ALU like this. So 2 comes in one side, 3 comes in the other side, and then control unit says, okay, ALU, add those 2 numbers I just sent you from memory. And then it adds them together. So it comes up with the result 5. And it's has to decide what to do. Usually that's going to go back to memory then. Write it then to back to memory. So write 5 back to memory. Yeah. And then maybe it's going to do something with that result too. So yeah, so the control unit's just sitting up there kind of like telling it, memory, this number, go to data path, okay, send that to I/O, send it back to memory.
So
what?
So the data path, what does the operation like? The adding, the
Yeah, so inside here, this is a bunch of circuits. And so if you want to add 2 numbers together, it receives a 3 and a 2, and it represents that with essentially digital voltage. And it has to add those together. So when it puts 2 voltages into a certain circuit, it gets out another voltage. That corresponds to another value. And so at the very heart of this is like actually circuits doing the adding. So like the 3 and the 2 get added together, an actual circuit is doing that adding. So there's like a voltage that flows through it and gives you the result. So yeah, at the very, very lowest level, it can't do very complicated things. It can do things like adding, and it can do things like comparing the size of 2 numbers, like which number is bigger. It can do that sort of thing. So you can write these digital circuits that can do these really simple comparison tasks or arithmetic tasks. And what DataPath consists of, a lot of it is just a bunch of those little building blocks. So it's got like a little, portion of its a portion of its circuitry that, for instance, will be able to do like a sum. Like this will be able to do a sum. You know, there's like little transistors and diodes in here. If you put two voltages in, it'll give you a voltage out that corresponds to the number that is the sum. So that's how, like, the actual, and that's why this is called, like, the brawn, right? So the brain is the control unit, and the brawn is the data path, because that's where, like, the actual stuff happens. Like, the plus happened there. Like, the actual addition or the comparison happens there. So the control unit wouldn't be able to do anything without the data path, but the data path wouldn't know what to do without the control unit. And then they wouldn't have anything to do anything on if it wasn't for memory storing the stuff. And then we wouldn't know anything about it unless we had input, or unless we had output. And there would be nothing to do anything with unless we had input. So, yeah.
So can the control unit send both after doing the operation? The result will be can send both to memory and then to the display at the same time.
Yeah, it can do that. It can do it. So depending on, and that's the thing, like, we start to get really hardware specific at a certain point, but data path can be used to, you know, go to I/O, or it can be used to go to memory, or it can do both operations. Sometimes you have to do that sequentially, like first send there and then take it and send it to that, which, yeah. So we're going to interact with this at a relatively high level, but being able to think about I/O and memory and a little bit of concept around this control unit and data path, but not as much. But definitely thinking input, output, thinking about memory, addresses, and how that works will come into play when we're writing in C. So, like there was the get care, put care question earlier today for C. And that's, get care is essentially reading an input, and put care is writing an output. And if you can use get care for something that's in memory too. But if it's from a keypad, get care is going to be an input. And then put care is usually going to be set to an output. So like our LCD screen. So we're going to be using that to, when we hit like the number 5 on the keypad, we want to see number 5 show up on the screen. So we have to use like C to say, okay, get the character and then put the character on the screen. Okay? All right. Let's go over to the lab and see, there were a couple questions on some hardware, so let's go over there and do that.